Okay, so we're going to do some examples of rearrangements just to kind of see how these reactions work. So I'm going to give you the starting material and the product. You can pause the video, draw some mechanisms and practice that, and then I'll go through the mechanism as well. And so and then we can compare. Okay, so the first one is we have this alkene and we react it with HCl. We get this product. So it's clear that a rearrangement has happened because the two carbons that were part of the alkene, the chlorine doesn't end up on either one of those. So this is your chance to pause and kind of try this out yourself and come back when you've got an answer, and we'll see what your answer looks like compared to mine. So what's going to happen first is the pi bond is going to come get the hydrogen, right? So pi bond is our base. Pi bond makes a bond to hydrogen. We break the hydrogen-chlorine bond, make a sigma bond, break a sigma bond, create a carbocation, right? This step is hopefully becoming second nature to you at this point. We put the carbocation on the more substituted carbon. We put it on the secondary carbon, not the primary, right? And now we have a carbocation, and so this carbocation can do a couple of different things. One, it can go back to the alkene, right? We've talked about that before. That's unlikely, or not necessarily unlikely, but non-productive, right? Instead, what we're going to do is we're going to rearrange this cation to a more stable cation because we have a secondary cation next to a tertiary carbon, right? So here's our tertiary carbon. Secondary cation next to a tertiary position, right? That equals rearrangement. So even if you didn't have the product, as soon as you make this carbocation, you would check and say, okay, I have a secondary carbocation. I need to look and see if there's a tertiary position nearby or next to it, and indeed there is. So now we're going to take this hydrogen. Sorry, I took too long to draw this. All right, I'm going to take this hydrogen and I'm going to move the electrons in that carbon-hydrogen bond over to the carbocation. So we're moving this CH bond. We're moving the whole bond over here. And so again, I'm going to draw this. I'm going to redraw my starting material just as is, and then I'm going to make the changes that I made here. So I'm going to redraw this and put a hydrogen at this position, which means that the carbocation is now at this position. So we've rearranged to make a tertiary cation. Right? The tertiary cation is more stable than the secondary. That's what allows this process to happen. Now, once we make that, now we can bring in our conjugate base, our Cl minus, right, that we generated in the first step. It's going to come in. It's going to make a sigma bond to that tertiary position, and we're going to end up with our final product. So in this case, pretty straightforward. These are the reactions that these are the conditions where rearrangement is going to occur when you have a secondary cation next to a tertiary position. Let's draw this one. Here's the next one. This time I'm going to use H2SO4 and H2O. And this time I'm not going to give you the product. I'm going to ask you to predict the product. So you can kind of work through this and see how things go. All right, so first things first, we're going to make this H plus. Pi bond attacks the H plus. We generate our carbocation. Again, our choices are primary position or a secondary position. And so we're going to choose to put the carbocation at the secondary position. So when we do that, now at this position, there's a tertiary position right next door. So once again, we have secondary cation next to tertiary position. That means rearrangement. So we have a secondary cation here, we have a tertiary position here. Right, so then this hydrogen, again, these CH electrons, the electrons in that sigma bond are going to move over. That means the hydrogen atom is going to move over as well. We're going to end up with hydrogen here and a hydrogen there. And now bring in your conjugate base, H2O, comes in to attack the carbocation, make a sigma bond at that carbocation, and we get the oxygen now attached to that position. And then we just have to lose H plus from this OH2 plus group here. We're going to get rid of that and make the conjugate base, and that's going to be our nice neutral product. So our nice neutral product is going to be something that looks like that. So hopefully that matches up with what you got, right? If you didn't do the rearrangement, you would have put the oxygen at this secondary position, but because there's a tertiary position next door, as soon as we generate this cation, we get the rearrangement to the more stable cation first. So the rearrangement happens first, then we bring in our conjugate base in order to make the new sigma bond. All right, let's do one more example. We're going to use HCl again. Same deal, predict the products, draw the mechanism, etc. All right, so this one is a little bit of a trick question because we're in a rearrangements video, but it turns out that when we make our carbocation, pi bond attacks the hydrogen, we break the hydrogen chlorine bond, right? When we make that carbocation, in this case, we don't have a rearrangement setup. We have a hydrogen here, we have a cation at the secondary position. So we have the secondary position, and next to the secondary position is another secondary position, right? So there's no rearrangement, whoops, possible here, right? Carbocations can't see the future. And so even though there's a tertiary position way over here, right, this carbocation is not close enough to rearrange that tertiary position. It can only rearrange to the neighboring position. Right? And you would say, well, can it rearrange here and then keep going? And the answer is no, it doesn't see that far into the future. So secondary versus secondary, there's no advantage to rearranging, and so it just doesn't. And so instead you get Cl minus comes in and attacks that carbocation, and you get a chlorine at the secondary position. This is a Markovnikov addition, right, where the hydrogen is added there and the chlorine is added there. All right, last example. This time we've got 3 methyl groups over here and a double bond, and we're going to use HBr. And the reason I wanted to show you this one is because this is an example where this time we're not moving a hydrogen, we're going to actually move a whole carbon-carbon bond in this case. And so what you get out in the end is this tertiary bromide. Now this looks like a completely different molecule than our starting material. So let's go through what happens. Right, if you want to pause and work out your own mechanism, you can do that here. So the double bond is going to attack the hydrogen. It's going to break the hydrogen bromine bond and generate our conjugate base. So far, so familiar. Okay. Make a secondary cation. We're going to have a hydrogen here, etc. Okay. Now, in this case, we have a secondary cation, and it's next to a carbon that is actually connected to 4 other carbons. This is a carbon next to a quaternary carbon. Right? And so when you have a secondary next to a quaternary carbon, this also means rearrangement. Rearrangement by moving a CC bond. Right? So in this case, we're going to move one of these methyl groups. Right? All the electrons in that carbon-carbon bond are going to move over here. The carbon that was the quaternary carbon has lost one of the carbons that it's connected to. Right? So now this CH3 group is over here. Right? So we had a CH3 group here. It's now moved over here, and that means that now this is a tertiary cation. So we can also make a tertiary cation by moving one of the carbon groups away from a quaternary center. And then, of course, from here, you bring in your conjugate base, your Br minus that we generated in the first step comes and attacks that carbocation, right? Adds a bromine to that position. That's how we get our final product. All right, so a couple rules here. Under strong acids plus pi bonds, right? We have to watch for rearrangement. We have to watch for rearrangement. We have to have, we're still following Markovnikov's rule, right? Where the carbocation goes, where the hydrogen goes. But once we generate that carbocation, we have to watch for rearrangement. So when you see strong acids, HCl, HBr, sulfuric acid, those kinds of things reacting with pi bonds, always keep in mind that rearrangement is a possibility. All right, the next reaction that we're going to talk about is one where we try to eliminate that possibility and instead have reactions that do not undergo rearrangements. So the next video will talk about how do we avoid having to worry about these rearrangements.